Alright, so now we have an exercise, which is sort of what we're doing is we're taking the inverse function theorem, and instead of applying it at a particular point, we're applying it on an open set. That's sort of what this boils down to. Okay, so we have this function f goes from a to Rn, where a is a subset of Rn, it's continuously differentiable, it's 1 to 1. Its derivative always has non-zero determinant. Okay, so basically what we're going to do is we're going to prove that we can apply theorem 2-11, the inverse function theorem, at every point in A. So first of all, since f from A to Rn is 1 to 1, it has a unique inverse, f inverse, which goes from f of A to A. Because what we do is you restrict the range Rn to just the image of A, and then the restriction of f to this range, if you restrict the codomain of f to its range, then you have a function which is not just 1 to 1, but now it's on 2, and so it's a bijection, and so you can invert it, and this inverse is unique. Okay, so now, given any y in f of A, we're going to prove that f is continuous and differentiable at y. No. We're going to prove that f inverse is continuous and differentiable at y. So given any y in f of A, we know that there exists a unique x in A such that y equals f of x. The existence of such an x is guaranteed by the definition of f of A, and the uniqueness comes from the fact that f is invertible. If it wasn't unique, then you wouldn't be able to invert f, because f inverse of y would not be it would not be a well-defined function. Okay, so by the inverse function theorem, which is theorem 2-11, there exists sets VW open sets. Whoa, that was not intentional. There exists sets VW open such that, so X is going to be in V, which is a subset of A, and f of X is going to be in W, which is a subset of f of A, and let's see what else. So I guess technically, now let's think about this. For the inverse function theorem, W is actually technically a subset of Rn, I think. Is that a problem? No, I don't think so. So I'll need to keep this in mind, but I think it's a quick change. So and f has a continuous and differentiable inverse, and we're going to call this fx inverse. And it's going to go from W to V. Now, basically the reason I call this fx inverse and not f inverse is that this is technically not the same function as f inverse. Because first of all, f inverse is defined from f of a to a. And this inverse that we've defined is defined from w to v. So just from the domain and codomain, they're technically not the same. Second of all, we haven't yet established any relation between this inverse and the inverse of f. However, by the uniqueness of the inverse, whoa, that was weird, for any point y, which is in both w and in the image of a, if we take f inverse of y, then that has to be equal to fx inverse of y. Right? Because, there has to, because f is 1 to 1, so there is a unique inverse at any point. So there is a unique point x. So let's hear f. So first of all, I guess I shouldn't be using y here. Let's call this z, inverse of z, so it's fx inverse of z. Okay, so z is in f of a, so there exists a unique w in a such that f of w equals z. Right, and the inverse has to be the same for both of these, because the only potential issue would be if so we have fx inverse, which is defined on w, and w doesn't need to be entirely contained in f of a, I don't think. But if there's a point outside of f of a, well, in fact, there can't be any points outside of f of a, because then fx inverse isn't even defined on those points, because you can't get there, because if you could get there, it would be in the image of f. Okay, so for all z and I'll just say w intersect f of a, but that is f of a, so I'll just say for all z and w, f inverse of z is equal to fx inverse. That did not carry over everything. There we go. Okay. Thus, f is continuous and thus f inverse is continuous and differentiable at at y, because f is. So basically, f and z, f inverse and fx inverse are identical on w. And so we also know that fx inverse is continuous and differentiable on w. And so f also needs to be, because it's the same function. This holds for all y in the set f of a, and so f inverse is continuous and differentiable on all of f of a. All right. So that takes care of showing that f inverse is differentiable, because it's differentiable at every single point in f of a. That's what we've proven. Now we want to show that f of a is an open set, and furthermore that f of b is an open set for every b which is a subset of a. Well, a is an open set. So if we just prove this for every open set b which is contained in a, then proving that f of a is an open set will be automatic. This part is redundant. Okay, so to prove this, there we go. Continuity of F inverse implies that the inverse image under F inverse of any open set in A is open in F of A. That's just one of the first things that we talked about when we talked about continuous functions. And this is sort of an essential theorem or an essential result of continuous functions in the when you talk about from the viewpoint of point set topology. So thus, for all B, which is an open subset of A, if we take the inverse image under F inverse of B, we get F of B, and this is open. And that's a helicopter, but regardless, that's what we need to prove for this exercise. So basically what we're doing is we're showing that you can, if your function is not, if your function satisfies the inverse function theorem requirements on an open set, then you can sort of glue all of the inverses together. That's like one of the parts of this. But the other part is that this also tells us something about the image of an open set, because with like point set topology and with like set theory, with a lot of category theory things, I think you have information about what the inverse image of sets look like. Like if you have a set in the there's a lot of results about if you have a set in the codomain which has a particular property, then the inverse image under F of a whatever the relevant homomorphism is, or morphism, I guess, in category theory. Wherever the morphisms are defined, I think I haven't studied category theory. I know mathematicians probably should, but I haven't. But anyways, I think morphisms are defined so that you have a particular property in a morphism is a function such that if you have a set property of a set in the codomain, then when you take the inverse image of that set, then that set has the same property in the domain. That's why like a continuous function in point set topology is a function such that the inverse image of an open set in the codomain is an open set in the domain. In measure theory, you say that a function is measurable if the inverse image under this function of a measurable set in the codomain is a measurable set in the domain, etc., etc. So basically, even though we have this, we don't usually get results about what if you have a set in your domain and you want to consider the image of the set under a function. A lot of times you don't have information about that. But this shows us that for nice functions, i.e. for functions for which the inverse function theorem applies on an open set, we actually can prove things about the image of open sets, which is more than we usually get. That's more information than we usually get from functions. So that's the usefulness of this exercise, and it actually is useful in the next exercise. But yeah, so that's I think that's one of the main points of this exercise, is showing us that. And yeah, that's it.